establish a network connection. Because I have the screensaver disabled, so the login box doesn't pop up.
Well, having the real-time, the actual real-time accurate is actually important in different types of system. So I just want to kind of bring this up because we are already quite there already. In authentication, this is a big deal because with Kerberos 5, okay, what happens is when after you authenticate, it gives you a token. The token is time sensitive. In other words, the time token basically says, yes, this person has properly authenticated, but it will expire within a certain number of seconds. So if your real-time clock is not synchronized with the real-time clock on the server, then you need authentication to authenticate, then you can get kicked out just like that because the two clocks have a skew. So in those particular authentication systems, you actually have to specify how much of a skew is acceptable. Okay, up to how many seconds can be a discrepancy between two systems. Right. Now we can go back and restart everything, including the This is a 640 by 480. I would say that's a little bit pixelated.
I can't see the pixels from here.
Let's make it so that you can see it. So, yeah, it's not really that good.
Looks like the lines are about 6 pixels wide.
Yeah. So that's why you have to switch to the next resolution, which is 1280 by 1040. But because the image is significantly bigger, it really takes a lot more time to get through USB to get a picture across onto this computer, onto the screen. And that's why we see that horrible lag, when I try to write something on that piece of paper.
Numbers magically appearing.
Yep. And then turning off white balance, seems to be actually turning it on. It seems to be flipped to me. All right. So getting back to here, after a long digression, we can now continue with the algorithm, okay? Because the main point is really the algorithm. How do we write an algorithm to print the values correctly? So now we have to go back to that particular point in time.
So do you use a different program to record your audio?
I use a different program. The program that I use to do the actual screen recording and the audio is called FFmpeg. It's a really obscure program, and the original purpose is for transcoding. But you can also use it for screen capture and stuff. All right, so we're getting back to the data structure, and now we can start to write an algorithm to solve this problem. So let's go ahead and open a new window to write the algorithm. Okay, we want to keep an eye on the data structure because it is important to look at the data structure as we write an algorithm. So we'll define a subroutine to print values in the BST in a sorted order. So the name of the subroutine is print BST. And since we are not really that concerned about line numbers, we'll just shrink it for now. All right. First of all, what do you think this subroutine needs in order to deal with a binary search at all? What do you think it needs? Well, I would think that it needs an array of nodes, okay, like T in this case. Does that make sense? Okay. So we'll give it, an array of nodes. Okay. By reference, we'll give it, a particular, array T. Okay, we'll keep the same name even. But now that we know about types or records and stuff like that, we have to indicate what T is. Okay, so we have to say T is an array of, in this case, I think it's just called node or n. Yep. So it's an array of n, which is a node. Let me just double check. No, BST node. Just want to be consistent here. BST node. Okay. So are we doing okay so far? As a parameter. But that's the only parameter that I need, because everything else I can just make assumptions. I can make the assumption that the first node in the array is the root of the entire tree. Okay. But there's one more thing I need to know is for this particular invocation of print BST, what is the root of that particular invocation? Okay, so in this case, it can be passed by value, and I'll just use R, and it's an integer, because to indicate which node is the root, R just has to be an index into the array. In this case, it will be an array from 0 to 4 to indicate which one is the root that I'm dealing with. Are we still doing okay so far? In other words, print BST as a subroutine is saying, give me a tree and tell me which node I am. Okay? And I'll deal with the binary search tree, including myself and all my descendants. But I'm not going to deal with the rest of the binary search tree. I'm only focusing on the part of the entire binary search tree, starting with me as a node in the tree. Is that okay so far? In other words, if you look at the picture that we have drawn, in this case, the subroutine can be basically starting here. In other words, in a particular invocation to print BST, I can indicate and say, you know what, the tree is pretty big, but you don't have to worry about the rest of the tree. You are this particular node with a value of 1. Deal with that particular subtree, and you're done. Okay, that's your job. Does it make any sense? So in this case, the subtree that we are dealing with is really only this portion. When I invoke print BST and specify the index to the node that contains a value of 1, that particular invocation of print BST only has to print 1 and 2 and figure out which order those two nodes have to be printed, and that's it. Then it can return. But guess what? Somebody else, the caller or whoever is invoking that particular invocation, is actually another invocation of print BST that will handle the next level up, and then there's another one to handle the next level up. So that's really the power of recursion, is I can look at a problem as a sub-problem of a much bigger one, but since the nature is really the same, I can reapply the same approach. The first thing I can do here, okay, is to check whether the index is right or not. So I can say if R as an index is less than 0, which means it is no longer a valid index, or R is greater than or equal to RT bar, then you know what? I do not exist. I'm not a node of this tree. It is equivalent to the -1 in the spreadsheet. Okay, remember the -1 for the left and the -1 for the right? That's basically saying, no, you're not any node in this tree. So if I'm not a node in this particular tree, I got nothing to do. Okay, so just to make it clear here, I can say you'll do nothing, and that's it. The else case of this conditional statement means that I am a particular node in this tree, so I got something to do. Remember from last time what we have to do? If I'm a particular node and I'm supposed to print this particular tree of a subpart of a binary search tree, the approach is print everything that is my left descendants, then print my own value, and then print everything that is my right descendant. So I'll go ahead and do it. Well, I already have a subroutine that can print the entire left tree. It is the very same subroutine called print BST. The trick is, what do I pass as R? T is okay, T is just T, okay, I'm passing that reference along. The trick is, what am I going to pass as parameter R? Okay, now this is going to look kind of complicated because it will look like this. T itself is an array, so the first thing I can do to the parameter T is index it. So I'm going to use a bracket to start that. Okay, what should be the index in this case? The only other thing that I have right now is R. Okay, so I have to say T bracket R to get to a particular node. Once I get to a particular node, I need to find out which one is my left child. Okay, so when you look up the record type, we have a left member, a member called left, which is the index of the left node to a particular node. So that's basically what we need, is to specify left here. That is going to specify the parameter R to the next invocation of print BST. Well, if you look at it, from the perspective of T bracket R is really just saying, who I am, and then dot left is who's on my left. That's basically what it is. Instead of printing my own value first, I'm telling the node on my left and say, hey, deal with yours first, and then I'll print my value. So what if left is -1? I don't care, because the next invocation will check parameter R to make sure it is within the right range before it does anything. So it's up to the next invocation to say, oh, okay, better stop now because I'm not a valid index into the array. But as far as I'm concerned, I don't care whether I have a left node or not. I'm just saying, print that. Okay. The next thing I have to do is to print my own value. T bracket R is me, and my own value is represented in the member called V. Then I have to print everything to the right-hand side, but you know already how to do it, because we just have to basically repeat the entire thing, except whatever is left previously is now right. So we just have to turn this to right, and if, and define sub, and now we have the recursive subroutine to print the values inside the binary search tree in order. Is that okay so far? I think I'll turn this into the next homework assignment. Well, think about how many invocations you have to deal with in this case. Just using exactly the same data structure that we set up already. Okay, so I'm gonna pop that up here. So I'm gonna use exactly the same thing. So the assignment will be available, shortly, sometime today.
Starting at 6. Starting with 6.
Okay, you start at 6.
So you have to invoke.
So if you're counting the number of invocations, oh, I forgot I got my toy. Okay, so when you're counting invocations, okay, this is your first invocation, and then that invocation will cause this to happen, then it will cause this to happen, and then it will cause this to happen. That's actually an invocation 4 corresponding to the left-hand side of the node that has a value of 1. But it will terminate right away because the index is -1, R is -1 in that case, so we just immediately return without doing
anything. Just return it. How would you specify that? Would you say false?
No, nothing.
Nothing.
There's no return value. Print BST is not returning any value because it's printing it to the screen or the console. So there's nothing to return. In other words, this invocation number 4 doesn't do anything. All it does is to get invoked, figure out there's nothing to do, and then immediately return. Okay? And then you have invocation number 5. This is invocation number 5. And then invocation number 5 will cause number 6, which doesn't have anything to do because there's no left child in this case. And then it will go back to here, and then it will go to invocation number 7, which also has nothing to do. Then we'll go back to invocation 5. Invocation 5 will have nothing to do. Then we'll go back to invocation 3. Invocation 3 is all done at this point. We'll go back to invocation 2. Invocation 2 will do an invocation 8. But there's nothing to do. It will go back to here. Then it will go back to invocation 1. Invocation 1 will then go to here as invocation 9. And then invocation 9 will go here as invocation 10. And should use a dotted line here. And then that will go back to here. And then it will go to invocation 11 here. Then the invocation 11 will go back to invocation 9. Invocation 9 will go back to invocation 1. And then the whole thing is done. So I'm already giving you a general idea of the number of invocations. But the actual number of lines involved here is not too terrible because because the ones with dotted lines, those are basically trivial invocations. Okay, you set up everything, you get into the subroutine, you go through the conditional statement. There's nothing to do. You just deallocate everything, go back to the previous one.
The dotted lines are deallocations. The dotted lines are deallocations.
No, the dotted lines are the ones that have nothing to do.
Oh, they have nothing to do
So
with ND.
they go to the conditional statement and then they just say, oh, there's nothing to do. The ones that are solid are the ones that actually have something to do, something to print, to go to the else of the conditional statement, basically.
Indeed, the dotted lines don't deallocate?
No, they do deallocate, just
They
like
do
any
deallocate.
invocation. Every invocation will deallocate at the end, but the dotted lines are the ones that do not have anything to print or any further invocations. Okay? So this will give you a pretty good idea of, when you are tracing, that should be, the way, to look at it. Any questions about, this particular example of a binary search tree? I think for the final exam, we can say, turn this into a non-recursive algorithm. The non-recursive algorithm or version of this is actually much more complicated than what we just saw. Okay, let me just kind of go back to the recursive version. It's over here. The recursive version is not really all that bad. In fact, you can optimize the algorithm and say, if r is greater than or equal to 0 and r is less than bar t bar, then go ahead and do it. So the conditional statement can be much simplified. I want to illustrate this because I want to illustrate when do you stop the recursion. So if I were to make this simpler so that you don't have to trace as many lines, I would have done something like this. Okay, let's just modify this. This becomes your new algorithm. I would just reverse the condition here. So I'll be looking for r that is greater than or equal to 0, and it has to be less than bar t bar. So this algorithm, this algorithm will do exactly the same as the previous one, but you can clearly see that if r is -1, you just skip the entire conditional statement, get to the end, and go, oh, there's nothing for me to do. Because it makes sense. Because when r equals to -1, you are not a node of this tree anymore, and what are you going to print? Nothing.
That's even better.
That's a little bit better. It represents the same logic, except in this case, on line 4, I specify when you have something to do instead of when you do not have something to do. Yep.
If we don't have an entry, like say it is equal to 0, what does that represent?
We don't have.
If it's 0, like if we have an entry 0, so we have 6, 3, 0, 10, something like that. Would that be like no entry, or would that be just?
You mean when r equals to 0?
Yeah.
When r equals to 0, that's how your main program or main subroutine should do it. The first invocation into print BST should look like this. Okay, when you have your first print BST invocation, it should be print BST. You pass along some kind of array, and instead of using the left of something, okay, I need to make this bigger. So instead of using left here, you basically specify 0 because that's our, oops, not that. I have to replace this entire thing with a single 0. Because the node corresponding to element 0 in the array is the initial root. That is the first node of the entire binary search tree. So that's why the first invocation to binary search tree, print binary search tree, has to pass the 0 to r, because that really is the true root of the entire tree.
Well, that goes with what you were saying, that it has to be.
Right, well, this is our convention, because the way we constructed the tree is to sequentially allocate elements in the array, so the first element has to be the root.
This kind of stuff is going to get
Hmm?
Is this going to get
No.
This is statute.
Well, you can trace something like this. I will give you the algorithm, and then you have to trace it. But
this
to
is like-
trace the algorithm doesn't mean that you have to understand what it's doing.
This is like the beginning of statute.
This is CISP 430 kind of material, but in this class, it's, once again, you don't have to come up with the algorithm or to analyze the algorithm. You just have to follow the steps. But I want to give you the exposure of something that you might find useful later on. So I'll see you guys on Tuesday. Have a nice weekend. And we're getting there to the end of the semester.
I have
Very
a
slowly.
question of critical importance.
Epic.
No critical,